Okay, hello everyone. Welcome to the second lecture. I hope you can all hear me properly. And well, it's okay if you can't see me as long as you can see the screen I'm sharing. Just let me know in the chat or let us know in the chat if you're having, oh yeah, you can hear me good. Okay, so today we're really going to get more into the C programming. We only just did a little bit of a, just a really basic program yesterday. It was only yesterday. So yeah, let's get into it. So yesterday we did do a lot of admin sort of stuff, but we did look at a first basic intro to C program and some Linux. And some of you by now might have already had a Tute lab, so you might have gotten to practice that already. Some of you will have that later in the week, but you'll all get on top of this stuff, I promise you. But today's lecture, we're going to do some exciting stuff because we're going to be able to store data in our programs. So we're going to start looking at variables instead of just having hard-coded messages that we're printing out. And we're going to learn how to print out our variables, read them in from the user, do some maths type expressions, and maybe constants. If we don't get through all of the lecture slides in a given lecture, don't panic. I'll always just put them over to the next one, right? I don't want to rush through stuff just to get through it all. So here's a link to the live lecture code. You can always go and follow along and download the code during and after the lecture, or you can just follow along with what I'm doing on the screen. It's up to you. Okay, so this is basically the first program we looked at. Does everybody remember what these first two lines do? Or does anyone remember? What are these first two lines? Yeah, someone's written comments. Yeah, a few people have written comments, very good. And the comments are basically for humans to read. They don't get executed by the actual computer, and they're for documentation. So when we look back on programs, or your tutor looks at your programs, or your boss or your colleague, it helps them understand what's going on. Okay, now what about this next line that says hash include angle brackets stdio.h angle bracket? What on earth does that mean? Does anyone remember? Header file, yeah, it is a header file actually, that's correct. But yeah, this is what allows us to use the stdio library. Yeah, so we're including a library so we can use it for printf, for example, and we'll be using it for a few other things today as well. So we're typically always going to have this line of code. All right, now I never really explained. Actually, I'm going to move over to code now. It's basically the same program. I've got more comments. And what I forgot to show you is there is another way to do comments in C. You can do multi-line comments like this. Okay, typically in this course, we won't use this style of commenting most of the time. We'll mostly use these two forward slashes, but you might see this around the place. It can be handy if you want to comment out large sections of your code when you're debugging, but typically you can just use these two forward slashes, but that is another way. I'll just leave that there. All right, so I never really explained what this int main void means, but we will explain it later. But basically, every time we write a program, we need to write this, and we put our code inside it for now. And this is where our program will start executing. I also didn't really explain what this return 0 means. And for now, we're always going to have that in our program as well. So in our main function, at the end, we'll have a return 0. And that means that our program has executed without any issues, which might not be the case, but for now we're going to assume it is and just always put it there. Okay, so later we'll sort of really go into the details about this, but for now, you're just always going to have this hash include, this int main void with the open curly brackets and the closing curly brackets, and that returns 0 as the last line. What you won't always have is what's inside this main. So you're going to put different things inside this main function depending on what you're trying to do. So in this example, we've got a printf because we're trying to print something out on the terminal. So remember, when we do a printf, everything between this opening and closing quotation mark is printed out on the terminal when we run it. Now, the actual quotes themselves, these enclosing quotes, they're not printed out. Does anyone remember what this thing here at the end is? \n. Yep, I can see a few people saying new line, which is fantastic. Yep, and it's an escape sequence. Perfect. So, oops, I just deleted it. There we go. Let's try and compile this program and run it. So hopefully you remember, we can't just run this C code. We've got to use a compiler which will turn it into machine code that the computer can understand. And in this course, we use DCC. And if you can't see this clearly, please let me know as I'm streaming it if you can't read the text. But we use DCC. The name of the program is hello_comp.c. And then we want to make sure we give our executable program a name that we're going to remember and, that makes sense to us. So we put -o and then the name that we want our program to be. Now, if it doesn't spit out a whole bunch of error messages, it compiled, and we can go and run it. And it's printed out on the terminal, hello comp1511 and comp1911. And somebody's asking, what's the difference between DCC and GCC? So if you've never heard of GCC, don't worry. But out in the world, there's a common C compiler called GCC. The difference is DCC, the one we're using, is built specifically for people learning C. It has a whole bunch of extra sort of messages built into it to help you debug your programs and to find sort of bugs in your program and help you. And that's the one that we're going to be using. GCC, you do it in a similar way, that's fine, but for this course, we want to use DCC. Yeah. Okay. Now, if I wanted to put more new lines somewhere, I could, just so you can see the effect of these new lines. I'll just show you. I changed my program. I need to save it, compile it, and then I can run it again. And yeah, that looks pretty ugly, but you can see, it's now spanning 3 lines. I'm going to get rid of these. All right, and I can put more printfs in here. Oh, I can't spell, but that's okay. Good, bye-bye. And when our program is running, it's going to execute these things line by line. So it'll do the printf on line 18, then it'll do the printf on 19, then it'll do the return 0 and just finish the program. So let's just see that. Oh, and I didn't put a new line in, and that's what it looks like when you don't put one in. Yeah, doesn't look great. Okay, so they're the basics that we did. Yeah, if I didn't put the new line in, yeah, it looks dodgy. Okay, now we looked at escapes, and \n is an escape character. Now here's a little bit of a brain strain. what is this going to print out if I compile this and run it? So if this is making you confused, this particular one, yeah, it is a bit tricky, but I'll go through it. What do you think it'll print out though? Okay, people are having some, I could see some correct answers here and some good guesses. Now, remember, backslash is a special character. If I type in a backslash, it's going to go and look at the character next to it to see what to do. So if I just put in a backslash on its own, it's going to confuse it's going to confuse C. So if I just want to print out one backslash, I put in backslash backslash to say, don't treat this backslash as a special character, just print me a backslash. So I have a backslash, it's an escape character. C looks at the next character, it's another backslash, so it's going to print out one backslash. But then I have another backslash, so it looks at the character after it, it's a quotation mark. Again, quotation marks are special characters because they mean something within our printf statement. So we can't just put one on its own. If we want to print one, we have to do backslash quote. So this here is going to print out one quote character. Oops, hang on. There we go. And now we're up to here. We've got another backslash. So we look at the next character. It's a backslash. That's going to print one backslash. Then we're up to here. We get a backslash. We look at the next character. It's an N. And we all know that that means go to a new line. Other things we could, so if we do it, let's just show you what it looks like. Oops, I forgot my -O. Yeah, so this is how, this is what it's going to look like. And you'll be working with this in, I think, one of the lab exercises where you're printing out, I think it's a cute bunny. All right, so that's the sort of stuff we did. You'll get used to these escape characters in time, even if they're confusing now. All right, so let's move on to the new stuff we're doing today. Now, we're not going to go into the depths of computer hardware. This is just one slide, and we'll talk about relevant things as they come up. But maybe you've heard of these things. When you go and buy your computer, you're often looking at the specs of the computer, looking at how fast the processor is, or how much RAM it's got, or how much storage it has. So this little chip up the top is called a central processing unit, or CPU. This is what is executing all of our instructions. So it's looking at the instructions, it's working out what we wanted to do, and it's doing them. And it's doing arithmetic and crunching numbers and all that sort of stuff. Now the RAM, this is what we call memory in this course. So anytime in our program we need to remember or store some data, so for example, if you were writing a game, you might have a player moving around on the screen, and you might need to store where that player is, right? Its position. So you might need to store that somewhere, and we'll store it in RAM, okay? And then it can be there for you to update and find where that player is moving around. So that's RAM. When we say memory, we're talking about RAM. Now, the confusing thing is, some people get confused anyway, between RAM and the solid state drive or hard drive. This is the thing that is persistent storage that stores all your data, like your long-term data, so your files. So if you turn off your computer and you turn it back on, your files will still be there. With RAM, that's not the case. So RAM is storing all of the data that the program that's running needs to access while it's running. And you know, if your program's just a normal programming running on your laptop, you turn off your laptop, the program's not running, it doesn't need that data in RAM. So this is temporary storage for while your computer's on. It disappears when your computer's off. And especially back in the old days, if you forgot to save your file, maybe everything was in RAM, but you hadn't saved it to an actual file. Anyway, the main thing that we need to know is that when we talk about memory in this course, this is RAM, not like files. All right. And yeah, RAM is just one more thing. You don't have to remember this, but RAM is a lot faster than the solid state drive, which is important for when we're running our program. But the solid state drive is a lot bigger. We typically, you'll get a solid state drive with 1 terabyte of data, etc. All right. Now, how do computers actually store data? Well, everything's in noughts and ones, which we call binary. Binary because there's 2 digits, there's a 0 or a 1. And, people aren't very good with binary. We're used to having decimal, where there's 10 different digits from 0 up to 9. And we don't like looking at noughts and ones. So in decimal, when you get up to 9, you've run out of digits and you start combining digits and you get 1 0 or 10, and then 1 1, etc. In binary, it's the same principle. When you're counting, you go to 0 and 1, but now you've already run out of digits, so now you go to 2-digit numbers, 1 0, 1 1, etc. Anyway, why we don't have to learn how to convert in this course? Why do we do it like this? Why do we use binary? Well, computer memory is just, and apologies to anyone that's like a physicist or an electrical engineer, because this is sort of a simplified sort of answer, but computer memory is just a bunch of on and off switches, and we can typically use 0 to represent off and 1 to represent on, and it all works out nicely with binary. And we call 0 and 1 bits. So we can have 1 bit of information and it could either store a 0 or a 1. But we often collect these together into bunches of 8 bits. So in 8 bits, we can store more information than we can in 1 bit, and we call 8 bits a byte, which I'm sure you've all heard of, and you've probably heard of kilobytes and megabytes and gigabytes and terabytes. When we get to terabytes, there's lots and lots of noughts and ones to store lots and lots of data. So just think in the background, no matter what we're storing, it is actually going to be stored in binary as a big bunch of noughts and ones. But we don't have to worry too much about that in this course. So when we're actually using memory in our programs, we're going to do it by creating variables. So when we create a variable, we need to give it a name, and we're asking for a chunk of memory, and we're giving a name for that piece of memory. So anytime in our program we use that name, it's referring to that piece of memory. Our variables have to store a specific type of data. So for example, there's a type called int, and that allows you to store integers, which are just, say, whole numbers. And depending on what type you're storing, depending on what type you ask for, you'll get a specific size in memory. So C will work out, oh, well, you want an integer, that's 4 bytes, here's 4 bytes, or whatever it is. And you can store data in there, and it's a variable, so you can go and change it whenever you like. So to start with, we're going to just talk about 3 simple primitive types. So we've got int, char, and double. So int is something we can store integers or whole numbers in. So 1, 0, 999, minus 42, they're all integers. Then we've got char. The char type allows us to create variables that can store individual characters. And you'll notice we put these individual quotes around our individual characters. So we've already seen the double quotes in printf when we're printing out like messages with lots of characters. When we're dealing with char and a single character, we use the single quote. So yeah, this is how we can store basically any character you could type in, uppercase, lowercase letters, punctuation, math symbols. You know, just when you look down at your keyboard and you see all the things you could type, we can basically store those in a char. Then we've got double, where we can store floating point numbers, which possibly the word floating point numbers doesn't mean much to you, but it's things with a fractional component. So we can store things like 3.14159 minus 0.001. And we could not store these as ints because they're not whole numbers. So if we need numbers like this, where we might have fractional parts, we store them in a double. If we don't need that, it's going to be better to store it as an int. Okay, so how do we use these types in our program? Well, first we've got to declare our variable, and when we declare our variable, we need to put the type. Oh, I've already got scribble everywhere. We need to put the type, and in this case, the type I'm saying is int, and then we need to give it a name, and in this case, the name I'm giving it is age. So when I do this, C sets aside a chunk of memory that's big enough to store an integer. And in my program, when I use, that says age. When I use the name age in my program, I'm referring to this chunk of memory. And there's a good question that I'll talk about in a minute in terms of types, but ints versus doubles. But once I've got this chunk of memory and I've declared it, I haven't actually put a value in there. So right now we say it's uninitialized, and you know, we shouldn't be trying to get the contents of this yet when we haven't given it a value. So after we've declared a variable, or when we're declaring a variable, we need to give it an initial value. So in this case, there's two slightly different ways depending on how what you're doing in your code. Either way is fine. In this way, we've asked for a chunk of memory. We've called it my age. Then on this line here, we're saying, let's make my age equal to 21. So that's putting the value 21 into this variable. So sometimes, because we've spent our whole life doing maths, we start thinking that these things are sort of a bit like equations where we can be rearranging them and stuff. But what this is saying is put the value 21, into that variable. Let's set that variable to have the value 21 in it. So that's doing it in 2 steps. Over here, we're doing it in 1 line. We're saying, give me enough memory for an int and put the value 21 in there right now. Either way, you end up with a variable of type integer called my age with the value 21 in it. And we call this equals the assignment operator. It sets values inside our variables. Is everyone okay so far with this? Okay. All right, now before we get too far with this, let me just talk about these names. So when you start learning to program, it seems like the names of your variables aren't very important, and maybe as long as your program works, who cares what you call your variables? But when you start using large programs, if you start calling all your variables A, B, C, D, E, F, G, or Darth Vader, I've seen, or just, you know, random silly names, you're going to get very confused very quickly. You know, your colleagues and bosses in the workplace would get confused quickly. Your tutor won't like it. So you need to get nice names. So if you've got a variable where you're storing an age, call it age. Don't call it A or B or C or D or something like that. If you're storing information about the radius of a circle, call it radius. Don't call it, I don't know, just some random name. It'll make your life easier. Also, take note of the fact that C is case sensitive. So if you have a capital letter, that will make it a completely different variable than if you had it a lowercase letter, for example. We also have a style guide that sort of tells you how we want you to name your variables in this course. And anywhere where you're programming, there'll be some sort of style guide. They might be different in different workplaces or whatever, and you need to follow that particular style guide. So we want you to follow our style guide. For now, we can look at it in more detail later, but for now, when we're naming variable names, we want them to start with a lowercase letter. And if we want to have multiple words, we want to split them up with underscores. So you can't, and we call this snake case, you can't have a space in your variable names. So if you want something with the equivalent of 2 words for your variable name, put an underscore between it. The other caution when you're creating variable names is that there's words that are part of the C language. So you don't want to use those words as your variable names. So you don't want to use int and double or return as your variable names. It's not going to compile. So yeah, that's just a word of warning. So yeah, the variable names are very important, as I said, for style. It makes it more readable. Now there's a whole style guide that you can go and look at. To be honest, I think looking at it right now would be a little bit confusing, but I just want you to know that it exists. And as we're learning new concepts, you can go, there's a link here from the course website. You'll be able to go and look them up and get more information about, you know, the style that we expect. I don't want to spend any more time today though, because we're just learning how to code. All right. So let's talk a little bit more about integers. So we can represent integers in the type int. It's a whole number. It doesn't store any fractional components. Commonly and on our system, each int takes up 4 bytes, and in 4 bytes you've got 32 bits. So if you're good at sort of your maths, if you've got 32 bits and you can have all of the different, you know, each bit can either be a 0 or a 1, you're going to be able to have 2 to the power of 32 different possible sort of bit patterns. So patterns of these 0s and 1s, which seems very big, but it's not infinite. And these 2 to the power of 32 different possible values, well, some of those values will be used to represent positive numbers, some will be used to represent negative, and then we've also got to represent 0. So we end up with a range of minus, I'm not going to read out this big number, minus this big number up to this positive big number. And you don't have to remember this, but the point is to realize it's not infinite. Like in maths, we can think of these numbers as going infinitely. But here, there are situations where you can get up to this maximum and go over it and, you know, cause massive problems. And we'll talk about that later. So just be aware of it. In this course, we're not probably going to throw problems at you that are going to cause you to go over that limit unless you've done, you know, made a mistake. But we do want to let you know that these problems exist because we can only store, you know, a finite number of possible values, and we can make our ints too large. Okay, I hope that made sense. The next type is called char. We've already spoken about it a bit. We put our character in single quotes. Now, the thing about char is that these are really stored as integers behind the scenes. So when I type in this A with a quote, what's really stored is some small number that is a numeric code that represents this letter A. So our chars are usually 1 byte. They can store small integers that represent characters. Now, you know, we don't have to memorize what these integers are, but it is good to sort of understand them. So actually, I'll put it here. So yeah, in C, the default character representation is ASCII. So some of you may have heard about this. If you haven't, don't worry, but I can type in ASCII on the command line with -D, so we only have to look at decimal numbers. And this shows me the code for all of the different characters. We can see we've got uppercase characters, there. We can see we've got lowercase characters here. Made a bit of a mess. And there's actually patterns that exist. So I can see that my uppercase A is 65, and please don't memorize this, but we want to get an idea of the patterns. And my uppercase B is 66. They're all next to each other. My lowercase a is 97. My lowercase b is 98. So this means we can actually end up doing some maths on our chars and say things like a plus 1 equals b. And I'll show you some examples later. All right, the other thing that's possible is, I'll get rid of my scribble here. If I look at A, capital A, and lowercase a, there's a pattern there. You know, if we look at capital A and lowercase a, capital B, lowercase b, can anyone see a pattern between the uppercase and the lowercase characters? Between those numbers that represent yeah, somebody's put 32. So if A is really stored as 65 and I add 32 to 65, I get 97, which happens to be a lowercase a. So we're able to add 32, subtract 32, and we'll see nicer ways to do it, but to convert, right? So there's lots of stuff we can do based on the patterns in this ASCII table, but we don't want you to memorize these values or type in, we don't want you typing 65 into your code when you could just type in, oops, A, which is much more meaningful for people. Okay, so that's a little bit more about ASCII. A little bit more about double before we get into some coding. Double stores real numbers, but it can only represent a subset of all the possible real numbers. So no matter how big, you know, how many bytes we used, it would only ever be able to represent a subset. Because, for example, between 0 and 1, there's an infinite number of real numbers. And between 0 and 0.1, there's an infinite number of real numbers. So there's no way to store all possible real numbers. So sometimes what we end up storing, and to be honest, a lot of the time, we end up storing approximations that might not be exact. And then we do maths on these approximations, which sort of can compound, you know, the little errors. So anyway, typically our double data type is 8 bytes. And we don't want to use double unless we have to. We prefer to put our integers in ints where we know there's not going to be any approximation errors. And we use doubles when we really need those fractional components. All right, so let's start coding with this stuff. So honestly, there's a lot of details there that you don't really need in order to write programs with these things, but sometimes they really come in handy. So in this example, I'll just run through this. I won't run it because it doesn't actually do anything as such that's visible when we run it. Okay, so and remember, when we're running our program, we're going sort of line by line in order. So first of all, we're declaring a variable. This is asking C for a chunk of memory. I'm just going to put this arrow to it, called my age. Now down here we're saying my age equals 21, and remember that's assigning a value to this variable. It's putting that value of 21 into the my age variable. Okay? And imagine, you know, our program was doing something useful. At some stage we might want to modify that variable, and that's what we're doing here. We're saying actually now my age equals 25. So the value that's in there gets overwritten and we end up with 25 in there. Okay, so this is why they're called variables. We can go and change their values. All right, now down here we're declaring another variable. This particular variable we've called radius. And we've said, let's make radius equal to 3.5. And down here, we've made another variable of type char, and we've said, let's go and put the capital letter B in there. Okay, the character. So this is just showing us how we can declare and initialize variables. Hopefully this is making some sense. Okay. So now we can create these variables, but what do we do with them? Well, the first step is we're going to learn how to print them out, and then we'll get into doing some maths and stuff with them as well. But let's learn how to print out the values of our variables. Now we're still going to use printf to print out the values of our variables, but now we've got these things called format specifiers, and they're different depending on whether you're trying to print out an int, a double, or a char. So if you're trying to print an int, you use %d. If you're trying to print something out as a double, you use %lf. If you're trying to print something out as a character, you use %c. And that seems kind of confusing to people at first because it looks like %d would be for double, right? No, %d is for integer, %lf is for double. You'll get used to it. Okay, but how do you use them? Well, down here's an example. I use printf. I still have these, you know, quotations that are enclosing what I'm printing. And here I'm saying, let's print out my age is, and this just means some integer. I'm printing out my age is some integer, then the new line. But you need to tell C what that integer is. So over here, I've put what the particular integer is that I want it to print out. So it says my age is some integer. It goes and gets the value from this variable, and it prints out my age is 21. Okay, so this %d matches this variable over here. All right. Here's some more examples. So here I'm trying to print, I'm printing out height is, and then I'm printing out an integer. and the integer should be listed over here, and there's an integer variable called height. So this is going to print height is 21 and radius is, well, we've got %LF. We go to the next variable, that's double, it's going to print out 3.5. So in these situations where you're printing out more than one variable at a time, they have to be in the right order. This %D has to match this first variable. This next % thing is a %LF. It has to match the next one, right? So they have to be put in the right order, and the types should make sense. And it should all match up nicely. If you don't, it won't compile. Like if you forget to put these variables in and you just have this, the C compiler will say, well, I don't know what these values are that you want me to print, and it won't compile. All right. The next example is possibly a little bit tricky. I've got a variable called letter, and down here I'm saying the letter, and I'm using %C. %C is going to print something out as a character, and it's going to go along to this first variable, and to print like that variable is storing the character capital A. So it's going to print out capital A as a character. But down here I'm using %D, and I'm also using this char variable. What do you think this is going to print? I've got a char, it has the letter capital A in it, but I'm printing it out as a number. Does that make sense? Yeah, so in this case, what it's doing is it's going to print out the underlying numeric code that every char has. Now, you probably don't often want to do this, and you don't need to have remembered that the capital A is 65. You don't need to have remembered that. So, but the thing is, yeah, it's going to print out the ASCII value for it. Typically, we don't want to do that. We just really want the actual character most of the time. Okay, so let me do some coding examples, and you'll have to help me out. And think of some ideas. Okay, so in this, we're just doing a bit of an exercise together. We want to create some kind of int variable. So what do we want to store in our int variable, and what do we want to name it? Has anyone got any suggestions? Also, for now, don't worry about what int main void means. For now, just type it in. It's good if you're curious, but if, you know, we haven't really gone into the details. But what do we want to store? What do we want to store in this integer? We're not calling it Darth Vader. Years, okay, years. Somebody's written years. But I'm glad you were listening. Now, sometimes if you were writing a Star Wars program, yeah, it could be relevant to call it Darth Vader. All right, let's say it's going to take 3 years to do your undergraduate degree. I don't know. But we could store some kind of whole number in here. All right. And here, this is declaring the variable and initializing it in one step. So now we've got a variable called use with the value 3 in it. Now, what could we store in a double? Any suggestions? Ah, so like the mark in something. So somebody wrote grade. Yep. I'm going to call it lab mark. There we go. So we can store something like that, and because it's a double, we can have fractional components. Yeah, wham. Yeah, all those sorts of things. Everybody's thinking about marks. Or pi. Pi, the maths pi, not the food pi. Okay, now if we want to print these things out, I can use printf, and let's just, I'll type in some text, years, and because I'm printing out an integer, I'll put %d, and over here I have to remember to give the variable name. And in the same printf, I might just print out the completely unrelated lab mark, but that's okay. And then I'll do a new line. And I have to remember to put this lab mark here, otherwise, C doesn't know how to read my mind yet. Okay. So let's compile this. It's always a good thing to not wait until you've written 10,000 lines of code to compile it and run it. If you've done some code that you can compile and run as you go, it's a very good idea to get on top of any bugs. I'll use this one. On top of any bugs, earlier. So let's compile it. I'll get rid of this window. Okay. Okay, yeah, so it's printed out years 3, lab mark 1.7. What do you notice when it prints out the double? So when I printed out 1.7, by default, when we print out a double with %LF, it'll print it out with 6 decimal places. So if it had more, it's going to round it. If it has less, it pads it with zeros. Okay. Does that matter? Not necessarily. Can we change it? Yeah, we'll see it in a minute. All right, let's declare and initialize a char variable. All right, this time I'm going to call it grade, and I'm going to put F. No, I'll put A. We'll give ourselves an A. And %C because it's a char and we want to print it out. Oops, that's wrong. There we go. We want to print it out, as is, as a, oh, what else have I done wrong? I haven't even done this wrong on purpose. Can anyone see what I've done wrong on line 20? I've used the wrong quote. So instead of using a single quote for a character, I typed in a double quote. I don't even know why. Okay, so let's compile that. Let's run that. There we go. All right, now just to show you what happens, I'm going to change this lab mark. So something like this. Then I'm going to print it again. Oh dear. Okay, but what I'm going to do is one of them I'm going to print it to 2 decimal places. So to do that, I can put a 0.2. If I put 0.2 before the LF, it will round it to 2 decimal places. I could change that to 0.1 or 0.20 if I wanted to see more significant figures. All right, so let's try that. Oops, I left off my semicolon. Yeah, and we can see that this one, yeah, it cut it off after 6 decimal places. And here you can see that if it needs to, it rounds. So it didn't type out 1.71, it rounded this up and it's printed out 1.72. So often you might want to do this when you're printing out your doubles. The percent is just a special character that we use so we can tell printf what to do. So it's called a format specifier. We put %d if it's an int, %lf if it's a double, %c if it's a char. Okay, we'll do one more example and then we'll have a break. But I've got this code here. It's got 3 variables. Basically, we're trying to print them out, but there's a bunch of errors in it. So even if you can see the errors straight away, and maybe you can, somebody's asked the $1 million question. How do we print a % if now that's a special character? Now, logically, you'd imagine we'd do \%, but yeah, it doesn't actually work. So if you thought of \% to print the %, yeah, we would think it would be, but apparently it's %%. So you can try that later, print, and let's do it now. Let me go back to this one that works. So again, if I just try and do this, it's going to complain and say, what? That's a special character. Where's, incomplete. For some reason, to print it, you do 2%. The \/ doesn't work. We can see it down here. So yeah, that comes up occasionally. That you actually, it might be quite common to print out % really. So it could come up. It's understandable if you don't remember that detail just now. Okay, so let's go through this one. This one, let's compile it, find the errors, and once we're done, we'll have a break. So this is what happens when you're doing your assignments and labs. You compile things and you get a whole big long list of errors and warnings. Some of these are warnings, which potentially means you could still try and run your program, but we want you to fix them all. You always scroll up to the first error. Now this is saying line 13. It's saying implicit conversion from double to int. So basically, we're trying to store 1.5 in an int, and we can't do that. Okay, what type should we use if we're trying to store 1.5? Yeah, double. So let's change that. And when you change something, it's always good to save it and recompile because early errors can affect later ones. Okay, and I'm going to clear my screen and do it again so I can find the first error. Now it's saying on line 16, there's too many percent conversions, more than there are data arguments. So if we go to line 16, yeah, I can see a %d and another %d, but I've only got one variable there. Now, looking at the text, it looks like I wanted to print out my value variable, right? So now I've got 2% Ds and two variables. Is there still something wrong with this though? Let's try. Oh, I can't, there's too many errors. I'm clearing it and doing it again. So again, line 16, I've got the right number of variables now. But yeah, one of them's supposed to be a double. So that should be an LF now. Okay, we've got one integer and one double. So let's try and compile that. Line 15, a square, it's saying sides is uninitialized. So I'm trying to print out the variable sides. I never even gave it a value. So we can't do that. We have to give it a value. Since it says we're talking about sides of a square, I'll give it the value of 4. Oh, yeah, so with patience and perseverance, we fixed all those error messages and warnings, and now we can run our wonderful program that, you know, doesn't really do anything useful. But that's the process you'll be going through, getting rid of your error messages. Can you give it a value with the print? I mean, you could hard code that the square has 4 sides, or you could do it here or something like that. All right, so let's have a quick break. We'll come back at about, I don't know, let's have just a 5-minute break. We'll come back at about a little bit after 5 past. Okay. Okay, let's get back into things. I think I've got my sound back on. Okay, so in all of the examples we've looked at, all we've done is hard code data into our program. So often we want the user, whoever's running the program, to be able to enter their own information, like how old they are, what lab mark they got, for example. So how do we read in data from the user? Well, it's similar to using printf, but we use scanf, and we still use %d, %lf, and %c. So, you know, once you've mastered printf, scanf's not so bad. The difference is that, you know, is very easy to forget when you're learning is when we use it, when we're doing scanf, we've got to put this ampersand before the variable name. We're not going to go into the full details of this, but this is giving the address of the variable to tell scanf where to put it. But for now, before we really go into addresses, for now, just always put this ampersand if you like. Well, not if you like, you have to always put the ampersand when you're using scanf, and you don't put it for printf. Don't worry if you don't really understand what the address is. We're going to talk about that in full depth in a few weeks. Okay, so yeah, I've got an age variable that can store an integer. I say scanf %d, and whatever the user types in, hopefully they type in an integer though. Imagine they type in that they're 21, that's going to go into this variable. Okay, so that's how we can do it. So here's an example of some scanf code. And I might go to the actual VS Code to have a look at it. All right, so this first part, that's the same as a slide. I've got 3 variables, one's a char, and I'm telling, it's always good to tell the user what you're expecting them to type in, right? So I'm saying, please enter your first initial. They get to enter their first initial. I say, please enter your age. Hopefully they enter their age. Please enter your height. Hopefully they enter their height. Then down here, I'm just printing it all out again. So we're just showing how to read stuff in and store it in our program, and then we're just printing it out. We will get to where we do something useful with them. I've compiled it, I'm running it. So when we've got a scanf, it's going to sit there, the program's going to sit there and wait for me or whoever's running the program to type something in. So if I don't type anything in, it's just going to sit there forever. I won't do that. I'll type in, it says, please enter your first initial. I'm going to type it in. It says, please enter your age. I'm not going to type that in, but I'll type in an age. It says, please enter your height in centimeters. I don't even really know. I'm going to make that up. So it's read all that stuff in, and then I've got a printf that's gone and printed it all out. Okay, does that make sense? Now, if you forget this, if you forget to put this ampersand with scanf, which you probably will do at some point, it's not going to compile, and you're going to get this confusing message. But yeah, when you're using scanf, you've got to put this ampersand. There we go. Now the other thing is, imagine, well, that you can't really go wrong when you're trying to enter an initial. Even if you type in question mark, it's going to accept it and think, fair enough, that's the initial of your name. But when scanf is expecting us to type in an integer, and what if we don't? What if we typed in hello or something? You know, users don't always type in the right thing. The scanf %d is just going to think, oh, I failed, there's no integer, and it's just not going to read anything in at all. And what that means is we'll end up with nothing in our age variable because I typed in hello, scanf didn't know what to do and just stopped reading any more stuff in. And so we got this. And now later in the course, we'll work out how to do checking for errors to see if the user typed in something suitable. But for now, you know, your program's probably going to crash like this. So just in case when you're playing around, you accidentally do something like this. Yeah, this is what happens right now, the way we're doing it without doing any error checking. Okay. So for now, we're going to assume everybody's always entering the appropriate, data. Okay. All right. So let's just add some more in. I've got two double variables that I'm using for an x and y for a point. And then I'm going to print them out, but I've got to do my scanf. Now, whether I do one scanf or two scanf, it's really going to make no difference. I'm just going to do one that reads them both in at the same time. And I've got to make sure I say X with the ampersand and Y. Okay, and I've said how X and Y and single letter things are bad names in general, but if you're talking about points in maths, X and Y might be reasonable names, you know, if that's what the coordinates are called. Okay, I'm going to enter this. And now it's saying enter X and Y. Now, just because we've got this in one scanf, it doesn't mean the user has to type it all in on one line. So I could type in the X coordinate, I could say minus 4.2. I could then have lots of new lines and lots of spaces. I don't know why I would do that, but I could. And it's going to read it in fine because when scanf is reading in numeric data, it just skips over any spaces or any new lines, any white space. Okay? So it just ignores all of that. Now, when we're reading in characters, that's not the case because a character could be a white space. You know, we don't want, if you were writing code for a text editor, you don't want to just ignore all the white space. It's important information. But if we're trying to read in integers or doubles, it will ignore the white space. Okay, now it can get a little bit confusing when you start off, or even not when you start off. If we've got this situation here, this situation is almost identical to what we had before, but we're reading in the age, then the height, and then the initial. So let's compile this. It's saying, please enter your age. Please enter your height in centimeters, and I'm just pressing enter, and suddenly the whole program's finished. I never even got to type in my first initial. So what's going on here? Oh, and people are asking, what if we enter a letter? If we entered a letter and we were supposed to read in an integer, it's just going to stop and not read it in and just give up scanning. So you won't get any data read in. But in this case, why did it scan in my 42, scanned in my 190, but then I never really got to scan in my first initial? What happened? Well, let's try it again. I mean, even if we had some stuff like this, that's all good. I press enter. Suddenly it doesn't, I didn't get a chance to type in my initial. Yeah, it scans the new line character. So as I'm typing in, so I've typed in 42. When we're reading in doubles and ints, it skips over this enter that I've typed in. But when I type in this and press enter, that %C that scanf reads in is this new line character. And you can even see we've got this new line here as my initial. So this is the thing that can be confusing when we're working with characters. It will take the new lines and spaces and read them in. It can be very confusing. Sometimes if we know we want to skip the spaces, we do this little trick here, and you will be doing this in labs. So pay attention. Instead of just having %C, we can put a space %C. Why? Just because this is how they decided to make scanf work. I don't think it's logical as such. Now, if we do that, now our scanf %C will also skip over white space. So something like this. Now ignored that new line I put in, and I can type in my first initial. So before, when I did it, when you do it like this with %C, I'll save it and do it just one more time. If I just type %C, when I run this, as soon as I press enter here, the new line character is going to get read into my initial. So I'm going to end up with an initial of new line because that was the next character I typed in. If I put a space here, this tells scanf to ignore any white space. Oops, I just typed in something that made it quit. Let's try that again. And so when I type that new line character in, it's ignored it, just because we put this space here. Okay, so you will do that kind of thing in labs. If you want to ignore the white space, you just put this space in front of it. Again, that's just a decision that they made when they were making scanf, that's what this would do. Okay, so it's a bit tricky, but hopefully you understand the basics of %D, %LF, etc. All right, so let's move on. And that's sort of just slides explaining what we've just done. Let's move on and actually start doing some expressions and calculations. So we want to be able to read in data. We want to be able to do all sorts of calculations and stuff like that. Now, a lot of these operators are things you're familiar with. So plus or addition, minus or subtraction, times, I guess, or multiplication. Now, usually when we're writing maths, we don't use this asterisk. but in C, the asterisk means multiplication. Then we've got division, and this percent doesn't mean percentage, it means modulus or mod, which is the remainder. And there's a bit of a warning with division. So in the world of maths, if I do something like 3 over 2 or 3 divided by 2, what do I get, like in the world of maths? It's not this part's not a trick question. So in the normal world of maths, I would get, what would I get, 1.5? In C, if I do 3 over 2, I get 1. Why do I get that? Well, if I'm dividing an integer by another integer, it does it as integer division. And when we've got integers, there is no fractional component. So an integer divided by an integer will always give us an integer. It doesn't round, it just chops off the fractional part. Okay? And this can cause a lot of confusion as well if you don't know it and or if you forget about it. Modulus gives us the remainder. So, you know, if you, I don't know if you did division like this at school where you'd say, what's 7 divided by 3? And you'd say maybe 2, remainder 1, stuff like that. But mod gives us this remainder. And integer division would give us this too. Okay. So these are our operators. Now, when we put together these things into expressions, the precedence is the same that you'd expect from maths. So precedence is sort of like determines the order of operations. So something with a higher precedence gets evaluated first. So, you know, multiplication and division have higher precedence than plus and minus, and they get done first. So you'd know this from maths. It basically works the same. Association is what we'd expect from maths. So that's whether we do it in left to right order. So for these normal operators, if we've got things that are the same precedence, yeah, we just go from left to right. Just like in maths, we can use brackets to force the order of operations. So here in this last example, we're forcing the addition to be done before the multiplication by using those brackets. So if you know all this from maths, it should be good. It should be the same. There's a whole table that goes through, and if you're really keen and interested, you can go and look up this table that has all the precedence and associativity for all the different operators in C. You probably don't need it right now with the operators, the few operators we've learnt. Okay, let's have a look at these arithmetic expressions. Let's have a look at this top left one. What is this going to print? Yeah, I'm getting a few 66s. Let's try it out. So we've got brackets here. So we're doing 3 plus 4, which gives us 7. Then we do the multiplication next. So we do 7 times 10 and we get 70. Then we do 70 minus x, which is 4, and we get 66. Okay, does that make sense? So we've got 3 plus 4, then we multiply it by 10, then we subtract x, which is 4, and we're printing that out. Okay. So let's have a look at this one. The next one down here, we've got char C1. Again, these are bad names, but these aren't proper programs that are doing anything useful. They're just examples. And we've got C2, which equals C1 plus 1. What on earth is this going to print out, this example here? I'm seeing quite a few numbers, and it depends what programming languages you've done before, potentially, if you've done any, as to what you think this might do. But keep in mind, I'll just do this again. When we store a character, what were we even storing? It was a lowercase a. When we're storing a lowercase a, what we're really storing, we type it in like this, but what gets stored is this ASCII code. Again, we don't have to remember what this is, but just to give you a concrete example, it's 97. So if I say a plus 1, what I'm really getting is 97 plus 1. 97 plus 1 is going to give me 98. If I print 98 out as a character, I'm going to get B. So this can be really handy that we can do this. All right. And we could do A plus 2 equals C, D minus 1 equals C, all sorts of things. Okay. So I do have a slide that explains it. So our characters are represented as integers. So it's adding 1, or in this case, we're subtracting 1 from the underlying code. So we can do maths on these things, and it moves us around the ASCII table. Hopefully that makes some sense. So this is really stored as 97. We add 1, we get 98, but we're printing it as a character, which is B. Does that make sense at all? But it's really good because then we can just think of A plus 1 is B, A plus 2 is C, etc. Now, what about this one over here? The third one that I'm just scribbling on. What is this going to give us? Okay, yeah, lots of people are writing 1. That's correct. This is integer division. We do not get 1.5. Oh, I think I just gave that example earlier, the same one. We get 1. It chops off the fraction. We print out 1. All right, what about this one down here, the one I'm now scribbling on? Okay, well, yeah, this is the very cruel and confusing part. We actually still get 1. I mean, it might be printed out with 6 decimal places, but we're still going to get 1. Why is this? How could this be? Well, the right-hand side, the expression is executed first. And when we're executing the expression, we've got 2 integers and we're dividing them. At that stage, when that division is done, we're already losing our fractional component. And now we're just storing the value 1 in our double. Yeah, and somebody said that's crazy. It's very weird at first. If you don't know and you're running programs and you're getting 1 for this, it can be very confusing. So that's why I'm telling you. Otherwise, yeah. So how can we control this division and get what we want? Well, the rule is if both of the operands or the things that you're dividing are integers, you're going to get an int. But if either one of them is a double, you'll get a double. So if I do 2.6 divided by 2, at least one of these operands is a double. So the whole thing will be done as double division. I'll get my 1.3. However, 3 divided by 2, they're both integers. I'm going to get 1. What's 1 divided by 2 going to be? One divided by 2 in the world of integer division is 0. But if I wrote it as 1.0 over 2, then I've at least got one double, and I'm going to get 0.5. If I did 1 over 2.0, I would also get 0.5. The other way to do things, because sometimes we've got variables, like if I've got x divided by y, and they're both integers, I can't just put a 0.0 on the end of it. What do? Well, this is where I can use something called a cast. So I could say, imagine, x and y are integers. I can say, please, please treat y as a double. This is what this means here. It's a cast. Please treat y as a double so I can, in this case, get my division with some fractional component. This is the only place in this course where you do anything like this. We don't want you to start saying, let's treat, all sorts of different things as doubles, just in this case. Hopefully that makes sense. You'll get tripped up on it from time to time, I'm sure, because we've done maths for so long. It's just instantaneous that we think of 1 over 2 as a half, right? Or 0.5. Somebody's asking about if we've got an expression with lots of divisions. At some point you're doing one division at a time. So at any point in time, if you're doing one division and those two things are integers, you're going to get an integer. If one of the things is a double, you're going to get a double. Okay, let's talk a little bit more about modulus. I've already talked about it and said, we call it mod. Looks like percent, but it gives us the remainder. Now, it doesn't seem maybe like it's going to be that useful, but it really is in computing. One common thing we can do with it is we can check if things are divisible by other things. And, for example, if I do a mod by 2, so for example, 10 mod 2 gives me 0. Because I get 0, I know that 10 is divisible by 2. If I know something's divisible by 2, I also know it's even. So you can use mod to do all sorts of things. One thing is checking if something's divisible or checking if something's even, right? So if I do 7 mod 2, I'm not going to get 0 because 7 is not divisible by 2 and it's odd, etc. So these things will come up as you're doing programming. And we just type it in like it's written up here. So we'd write 10% 2, and that means give me the remainder when we divide 10 by 2. Okay. Now I will leave these as an exercise for you to try. Try and work out what these examples will do and what they're going to print out, just to see if you're on track with your divisions and your mods. And you can code it up, or you can use the code that I've already coded up. Now this is the one we were talking about before. I'll just run it for you so you can go and change numbers around and play around with things if you like. But just to show you that we did indeed get 66, a plus 1 did give us b, 3 divided by 2 did give us 1, even this version of 3 divided by 2 did give us 1. And here you can go and again run through this like an exercise and see what all these different variations give. Just one thing here is, you know, you're going to have to compile this and run it and then comment it out and uncomment the next part. Sorry. But I just wanted to show you in VS Code, if I like highlight this and I've written it up here, I can press Control/ to comment my code. I do it again to uncomment it. So that's just something interesting to play around with as well. Okay. So what's the time? Yeah. No, I'll talk about this. No, I won't. Let's just do a quick Kahoot. Okay. I've been talking for too long. Let's do a quick Kahoot. It's just a small one. I don't know if you can hear sound. I can't. Oh yes, I can. So everyone, if you can just join, I'll start in a couple of minutes. This is just basic C stuff. Don't worry, it's not for marks, but if you do happen to win first, second or third, take a screenshot of yourself winning. You can come and get some chocolates in the next lecture. Okay, just one more minute in case anyone else joins and then we'll start. Okay, I think it's flattened out. Let's go. Yay! Lots of people got this right. Yeah, there's a few people, like these are all supposed to be tricky. Nearly all the symbols are there. The brackets are just in a different place. Okay, cool. This is something you will get used to after you've typed it in, you know, millions of times. Okay, and you're all very fast as well. Okay. This is multi-select. There could be more than one. Ah, yeah. Now, these were both correct. These are two ways of doing comments. We'll typically be using, the 2 forward slashes. And yeah, there's so many instances in C where you've got forward slashes versus backslashes. It's very easy to mix those things up. But again, you've only been doing this for 2 days, possibly. Okay. And after you've had labs, and you'll know it for sure. Wow, people are going pretty well considering it is, day 2 of this. Hash include, angle brackets to AOH. Yeah, again, just something you've got to get used to and remember. Amazing. Everyone got it right. Amazing. Fantastic. And that's important because printf is something we're going to be using all the time. So well done. A majestic panther. It's going well. Amazing. People are doing very well. Yeah, slight differences in some of them, but very good. Oh, delightful seahorse is coming up. I kind of mentioned this once today. I wouldn't blame you if you don't know this one. Wow, program executed successfully. Very good. A lot of people got that right. We haven't spent much time talking about that at all. Is there more questions? Oh. Again, this is a multi-select. There could be more than one right answer. Okay, so these were the 2 correct ones. It doesn't really matter in what order you do these, but what does matter, the part that matters is you've got the -O next to the name. Okay, so here we've got the -O next to the name that you're going to give it. Here we've got that next to the actual C file, which is not good because it's saying let's, we're trying to create a file with the program to run in it over the top of the C file. DCC won't let you destroy a C file though. So that's wrong, but that's why we've got to have the -O next to the name of the file or executable we're creating. And here it would have needed a -O here. Okay. Last question. Okay, excellent. So yeah, we're not running our .c files. We run the executable file that we create. And yeah, again, another situation where we've got, you know, a forward slash. It's so easy to get our forward slashes and our backslashes mixed up. We're all going to end up having dreams about backslashes and forward slashes. Okay, excellent, everyone. If you do win and you're coming in face to face on Monday, please take a screenshot, come up and get some chocolates or Skittles or whatever you prefer. Prairie, squid, whoever you are, well done. An adorable lizard, and oh, if you're a runner-up as well, get a screenshot. And proud mantis and etc. All right. Yay. Thanks everybody for doing that. The kombucha. Well done. A lot of those were so tricky because they were so similar. All the options are very similar. Just before we go, we do have a few more minutes. I want to talk about doubles and double precision. So I talked about this a little bit before. There's no such thing as infinite precision when we're trying to store data in our program. Or at all. Like, we can't precisely encode a simple number like 1/3, right? So when we do 1/3, even just on a piece of paper, we get 0.3333333 infinitely. So obviously we can't store that in a finite number of bits. And yeah, and even with numbers not like that you'd be surprised, I'll show you in a minute, often we can't store it precisely in binary, right? Because we're storing things in binary. So once we've got approximations in the numbers that we're storing and we do maths on them, the errors compound with, you know, the more and more we do operations in it. Yes, somebody's asked about mod. Okay, we will do some more mods. But yeah, I'll just finish this for now. So I just want to show you this example here of types. So here I've got my double. I've typed in 0.3, and we know that there's probably going to be some issue with that. But then I've just typed in 0.1. That should be stored accurately, right? Oh, please don't. Oh. I thought I was going to be disconnected for a second. So when we print this out, what are we going to get? I'm printing it to the default 6 decimal places, and then also I'm making it bigger. I'm printing it to 20 decimal places. So when we print it out to 6 decimal places, 0.3 looks fine, and 0.1 look fine. But when we print it out to more decimal places, we see that it's not exactly 0.3, and it's not even exactly 0.1. And neither of these things are being stored precisely. And if we start doing lots of maths on them, we don't get precise numbers. Okay. So, and this can happen even with whole numbers as well, with doubles, especially large whole numbers. It might give you the nearest approximation. So we really don't want to use doubles unless we really need to. And we'll talk about them more later in the course as we show you extra things where they might be problematic. The other thing we talked about was integers, that we have a finite range for integers. So yeah, we can store integers precisely, which is great, but within a limited range. And in the slide, or if you Google it, this is the largest integer that we can represent. You're not expected to memorize that. And there's ways of getting it without remembering it in your code, but here I've just typed it in. So what happens if we add 1 to that, or if we add more than 1 to that, what's going to happen? Well, if this is the biggest number we can store and we add 1 to it, we actually call it an overflow. With our compiler, DCC, it'll actually warn us. We'll actually get a runtime error. Let's have a look. It's saying you took the biggest number we can represent with an integer, you tried to add 1 to it, we can't represent that in an int, and it gives a runtime error and it stops. If you use other compilers, this might not happen. In fact, it won't happen. What will possibly happen is that it'll just wrap around to the most negative number. So you'll have a really large positive number, you'll add 1 and you'll get some large, or do we call it small or big negative number. So you can get just weird answers when you start overflowing things. Or if we're using our system, you get a runtime error. Yeah, it goes like a circle, like a clock. So when you get around to the biggest number on the clock, you go back to the beginning again. So here, when you get to the biggest number, it just goes around to the smallest number. On other systems, ours just stops you and says, hey, because, you know, if you've got a big program and it's doing lots of calculations and it just spits out some wrong answer, you mightn't even notice, or you might not know where it comes from. So it's good that DCC helps us. DCC helps us by throwing an error. An error is more helpful and easier to debug than just a wrong answer. Okay, so yeah, just before we go, there's been some disasters. There was a Boeing 787 that had an integer overflow. It wasn't running DCC, but every 248 days, because that sort of corresponds to the maximum integer value, if we're talking about the hundredths of seconds in 248 days, every 248 days it'd have an integer overflow and it'd need to be rebooted. Another thing was there was a rocket, Ariane 5, that had an overflow, the rocket exploded. The other thing, which is a bit ridiculous, I don't know if you're too young to remember this song. Do you remember Gangnam Style and the video? That video was so popular, YouTube didn't realize that, you know, an integer wasn't big enough for its view count. And the number of views maxed out and their integer overflowed. They're now using 8 bytes to store their views, I think, instead of 4. Yeah, that was your childhood. Well, it was all your faults for watching this video again and again and maxing out the view count and having an integer overflow. So these things can happen. If it's a Gangnam Style video, you know, that's funny. If it's a rocket exploding, not so funny. If it's somebody's medical appliance or medication, not so funny either. Okay, all right, that's all I'm going to do today. We're not going to have time to do constants now. I didn't think we would. I'll let you go. We're all hungry. We all want to eat dinner. That might not be true, but it's true for me. So have a great night. I'll see you next week, either in person or online. And yeah, go watch Gangnam Style again tonight. See if you can overflow the 8-byte integer. All right, see you next week. Oh, and feel free to give feedback. You know, if the text was too big, small, if it was confusing in some places, too fast, too slow, whatever. See you later, everyone. Oh, I forgot to do modulus.